Hello, Physics 20 AP students. In today's lesson, we are going to get started on the Physics 20 Advanced Placement unit dealing with rotational motion. And we're going to do that by talking about different ways we can model objects and then starting to introduce a bunch of physical quantities that we can use to describe the rotational motion of an object. We're going to focus on kinematics quantities today. So we're going to begin by talking about two different models we have for objects, starting with a point particle. Believe it or not, for the most part in Physics 20, whenever we speak of an object, whether it's a box or like a ball or something of that nature, we're actually modeling the object as being a point particle. So what exactly is a point particle? It's an object whose size and shape is irrelevant. Why is its size irrelevant? Well, it's just a dot, okay? A dot doesn't really occupy any space aside from like just a single point. And its shape doesn't matter either, because if you took that dot and you rotated it by any angle, it would still look like the exact same dot. So irrelevant shape to it as well. All of our mass in a point particle is concentrated at a single point. Well, that goes without saying because our object is a point. A point particle can only undergo translational motion. Translational motion means motion in a straight line where you go from point A to point B. Or I've said here, motion from one point to another. Okay, so it can just move from one spot to another. And again, that's why we've looked at most of our problems in Physics 20. Motion of an object in a straight line, although we did have motion of object with projectile motion moving with a parabolic trajectory, we can still break that down into an X and Y direction in terms of the motion of the object. What we're interested in now in advanced placement physics is how rigid bodies move. Okay, so you can see here a rigid body now has shape and it has size to it. So I've drawn, this could, for example, be like the rigid body we're looking at is just some kind of circular object. So it does have size and it does have some shape to it. I mean, shape, I could replace it with like a box, in which case it would have like, obviously the shape would be different. But we now do care about the shape and the size. When I say a rigid body is a body that just, regardless of what forces act on the body, you cannot deform it. So you can't take the object and you can't bend it into a different shape. So we're going to assume it's kind of fixed with whatever shape it actually does have. Later studies in engineering anyways, we started to get into models where we actually could deform the objects, but that came well after looking at all of our kinematics and dynamics, all of our different physics principles associated with rigid bodies. The big thing about a rigid body is that, yes, it can undergo translational motion, which means it can move from one point to another. But the other key thing is that it can also rotate. I mean, a dot can rotate as well. A point particle, I suppose, could rotate, but it just looks the same. It doesn't make a difference. If you had, for example, this rigid body, and let's say that I just labeled this as 0.1, and you rotate it a little bit clockwise, well, that 0.1 is going to rotate along with the rest of the rigid body. So the rotational motion is actually quite important as well. So it can translate, go from one spot to another, and it can also rotate at a particular angle. We're going to focus on rotational kinematics. And you're going to see there's like a really nice analogy between translational kinematics. So translational kinematics was motion in a straight line, and rotational kinematics in terms of all the different equations that we did use. So we're going to start off by just going through introducing a bunch of these quantities and looking at some equations we can use to calculate them. Okay, so here's what we're going to start off with. So we have a rigid body. It's a circular rigid body. So it could be like a disc. And we're going to focus on point P on that rigid body. And what we're going to do is we're going to take this disc and we're going to rotate it about a central axis of rotation, which I'm going to refer to as O. So what that means is you can envision like taking your finger and then like just like holding the disc right at like with your finger, okay? And if you just kind of like hold the disc with your finger at point O, you can then take the other part of the disc and you can rotate it about that point. So the point in which all other parts of the rigid body are rotating, that's what we call the axis of rotation, okay? And we're going to label it as point O. First quantity we're going to identify is the angular position of, specifically we're going to look at point P here. The angular position is the angle between a line, R. The line R is going to represent the radius of the circle that connects O to P. So from O to P is the radius, and a specific reference axis. Okay, so the O to P is going to be represented by the radius of the circle. And we're going to make our reference axis just the positive x-axis. So the horizontal axis that points towards the right. So any angle we're going to measure relative to that axis. This is the same reference axis we would have used in RCS notation when talking about two-dimensional vectors. So in the first case, well, since that line that connects O to P is on the reference axis, we would say the angular position of point P is 0 degrees. In the second case, we'd be measuring an angle from the reference axis to that line connecting O to P, and I'm going to roughly say it's about 45 degrees. The other one, we have the line below the x-axis. There's actually a couple ways you could write it. You could write it as, I suppose, negative 45 degrees. So a positive angle means we go counterclockwise, and a negative angle means we go clockwise. We could also represent that angle in the third diagram by, I believe, a 315 degree angle. B, the angular displacement of the object. So you'll recall back in the 1D kinematics unit, we defined displacement as being the change in an object's position. Okay, so we have, again, our rotating disk with point P on the outer edge of the disk. Theta I is going to represent the initial angular position of point P. And again, we're measuring it using that line connecting O to P. We're then going to take this disk and we're going to rotate it counterclockwise. So that's going to cause point P on the outer edge of the disk to rotate counterclockwise somewhere in, somewhere in this direction. So it's going to rotate it a bit more towards this location. So perhaps it's over here now. So it's now at this point. We're going to call theta F the angular position of point P after it's rotated, its final angular position, which again, you're always measuring that angle from the reference axis to where that point is now located. Delta theta would represent your change in your angular position. That's your angular displacement. So it just shows like when you started at theta I and went to theta F, we swept out an angle that is delta theta. The other thing we're going to identify, let me just erase this here, is we're going to identify what distance did point P cover when it went from this point to this one right here. We're going to use the variable S to represent that. This variable S is what we refer to as the arc length. Okay, an arc length is kind of like a curved distance that you do cover. So if I want to calculate the angle swept out by line R as it rotates through an arc length of S, so it just means that we're going to start with this arc. We're going to go in this direction, And then when we do that, we're going to sweep out this angle that's going to be covered in here. Okay, and I want to know what delta theta is. Well, one way you could calculate it would just be theta f minus theta I. Okay, a change in a quantity is always a final. Looking at your final position minus your initial position. However, there is another way to calculate this in terms of both the radius and the arc length. So we can calculate the angular displacement by taking the arc length that has been covered and dividing it by r. So delta theta, your angular displacement, is the arc length divided by your radius. Few notes about this. 1. Theta is measured in a unit that is referred to as a radian. When you start to get into angles in higher mathematics courses, like I believe Math 20-1 or 30-1, you're going to start to look at angles being expressed in a unit called a radian as opposed to a degree. So what's the connection between a radian and a degree? Well, first of all, when we use theta in equations, it's going to be just simply a unitless quantity. 2, for a line r that sweeps through one complete circle, theta would be 1 revolution. So 1 revolution is going around the circle 1 time. That would sweep out an angle of 360 degrees. And the equivalent way that we represent this in radians is if we cover an entire circle, we sweep an entire circle, we say it sweeps at an angle of 2 pi radians. So the important thing about this is just identify what the, I suppose, the ratio is between degrees and radians, which tells me that in 2 pi radians, there is 360 degrees. Okay, that's what 2 pi radians would be equivalent to. I just did want to point one thing out here. Okay, so let's say we actually did. Let's use this equation. So we have delta theta is equal to S over R. And let's go through 1 revolution. So 1 revolution would be equal to 2 pi radians. For 1 revolution, what's the arc length that we cover? Well, the arc length we would cover would just be equal to the circumference of the circle. Circumference of the circle is kind of like your perimeter of the circle and going around, or the distance covered by an outside point going around 1 revolution. Now look what happens if I sub some numbers into the equation here. So delta theta for 1 revolution would be 2 pi. And this would be equal to S, which is the circumference, divided by R. If I bring in the R up to the top, it would tell me the circumference is equal to 2 pi times R. So I can actually use the arc length equation to derive the equation for the circumference of a circle. Although we're not always going to look at arcs that go around the circle once. It could just be part of a circle in terms of the arc length does cover. We need some sign convention for talking about angles. We've already briefly mentioned this. To identify the sign convention, we're going to use something called the right-hand rule, which is going to be perfectly consistent with the RCS notation we've already used. Here's how the right-hand rule works. If right now you took your pencil and you just wrapped your fingers around your pencil, and you stuck your thumb just straight upwards, okay? And then if you looked at the curl of your fingers, okay, so look at the curl of your fingers when you have your right hand that's wrapped around your pencil and your thumb's pointing towards the top of the page. You should notice that the curl of your fingers, the direction that your fingers are pointing, points in a direction that is counterclockwise. So you would take your thumb and point it out of the page at you. I find it easier to do if you can actually wrap your fingers around something. And then the natural curl of your fingers should be counterclockwise. Just envision what direction your fingertips are actually pointing. Therefore, using the right-hand rule, we use whatever direction your fingertips point to be the positive direction. Therefore, your angular displacement would be positive when we go in a counterclockwise direction, and it'd be negative when we go in a clockwise direction. Again, this already matches the RCS notation. So the RCS notation was If you go counterclockwise, we're talking about positive angles. If you go clockwise, we're talking about negative angles. So nothing new. It's just we use something called the right-hand rule to make reference to this. And in physics theory, we're going to talk a little bit more about the right-hand rule. Well, we talked about angular displacement. So let's go from displacement to velocity now. Angular velocity we're going to represent with the Greek letter omega. That's a lowercase omega. It's kind of like an italicized W. So what exactly is angular displacement? Again, we have these perfect analogies between linear motion and rotational motion. So if I talked about translational motion, what velocity is, I'd say velocity is the rate at which your displacement is changing. So what would angular velocity be? Angular velocity would then be the rate at which your angular displacement is changing. Or as I've worded it here, the angular displacement of a rotating rigid body over a specific time interval. So we can calculate it by omega is equal to delta theta over delta t. And delta theta could be expanded to theta f minus theta I over t. And again, I just want to draw the perfect analogy to linear motions. For linear motion, we would have defined velocity as v is equal to delta d over delta t. Delta d, your displacement, represents the change in position of an object, which we can use delta x to represent. And then if we expand this, I guess we'd write delta t here, delta x would then be xf minus xi over t. So instead of instead of v, we have omega. Instead of delta x, we have delta theta. And then delta t is the same. It's still the same equation in terms of its format. It's just we're talking about rotational motion as opposed to linear motion. The units for angular velocity would be in radians per second, which you can see by the equation, because delta theta, we want to express in units of radians, and time would be expressed in units of seconds. Therefore, you'd have radians per second for your units for omega. Okay, let's take a step up now and go to accelerations. We're going from displacement to velocity to acceleration. Angular acceleration is represented by the Greek letter alpha. Lowercase alpha looks kind of like a little fish symbol. How would we define acceleration in terms of linear motion? Well, in terms of linear motion, I would say that acceleration is the rate at which your velocity changes. Therefore, angular acceleration should be the rate at which your angular velocity is going to change. Or the way I've worded it here is the change in the angular velocity of a rotating rigid body over a specific time interval. And we can calculate it by alpha is equal to delta omega over delta t is omega f minus omega I divided by t. Again, we have this perfect equation, this perfect analogy equation for comparing rotational to linear motion. So for linear motion, we'd have acceleration is defined as the rate at which your velocity changes. So delta v over delta t. Delta v can be expanded to vf minus vi. Divide this by t. So instead of linear acceleration, angular acceleration alpha. Instead of linear velocity, we have angular velocity, which is omega. And the units here would be radians per second squared. That's because the numerator would have units of radians per second for angular velocity. Divide that by another time unit, and it would give you radians per second squared. And the sign convention for omega and alpha is the same as for delta theta, which just means that if it's in the counterclockwise direction, it's positive, and if it's in the clockwise direction, it is going to be negative. It will take us one step further, then just end the lesson by looking at two example problems and speak about the special case of uniform angular acceleration. Once again, the equations that we have for angular or rotational motion are going to be identical in format to that for linear motion or translational motion. Okay, so let's look at some of our translational equations and look at the rotational equivalent. Okay, so we already looked at this one. For translational motion, acceleration is delta v over delta t. If you write the rotational equivalent, it would be alpha is equal to delta omega divided by delta t. How about this one? D is VIT plus 1 half AT squared. Well, angular displacement is delta theta, and angular velocity is omega. Angular acceleration is alpha. Therefore, it would be delta theta is equal to omega IT plus 1 half alpha t squared. So all we're doing is just, as long as we know that your displacement, your linear displacement is your angular displacement, your linear velocity or translational velocity is omega, and you know your acceleration is angular acceleration alpha, you can just rewrite the equations in the identical format. So if we had VF squared equals VI squared plus 2AD, that would turn into omega F squared equals omega I squared plus 2 alpha times delta theta. D is VF plus VI over 2 times T would be delta theta equals omega F plus omega I over 2 multiplied by T. And I think the only other one we don't use it very often, is D is VFT minus 1 half AT squared. So that'd be delta theta is omega FT minus 1 half AT squared. You might be wondering, why doesn't the delta theta have a vector sign above it? Because we're talking about angular displacement. Displacement's a vector. There's some kind of really technical explanation as to why delta theta is not a perfect vector, because there's some kind of rule that it doesn't quite meet. So I didn't put the vector sign here. However, in the way we're going to look at problems, we're going to totally treat it like a vector. So if you want to write the vector sign above it, go ahead. If you don't want to, then that's fine. I'm not going to provide the explanation as to why it's truly not a vector, because it involves a little bit of I want to say it's a little bit more complicated mathematical properties, which we haven't talked about, I think, in Physics 20. So we'll leave that. All right, example 1. So it says problem 5 from page 225. That's just the AP textbook that I sometimes pull problems out of. You don't need to worry about having a copy of that textbook. I'll just simply make reference to problems when I actually do use them. All right, so I have a CD that has a playing time of 74 minutes. Okay, so that is going to be delta T. Now I'm going to immediately convert that into seconds, because it does want the answer in radians per second squared. So if I convert that, I know that there's 60 seconds in 1 minute. And then that would be equal to 4,440 seconds. Okay, so that's my delta T. It says when the music starts, the CD is rotating at an angular speed of 480 revolutions per minute. Okay, we're going to assume we're rotating in the positive direction. So let's say assume rotation is counterclockwise. It doesn't really talk about what direction we're dealing with. Okay, so it says initially, so that'd be your omega I. So your omega I would be, we're assuming we're going in a counterclockwise direction, so that'd be positive 480 revolutions per minute. If you ever see the abbreviation RPM, RPM is an abbreviation for revolutions per minute. So we have 480 RPM. Now it says at the end of the music, the CD is rotating a little bit slower, still in the positive direction. And it's now rotating at a speed of angular velocity of 210 revolutions per minute. Okay, and what it wants me to do is it wants me to calculate the angular acceleration, the magnitude, as well as drop the direction at the end, and I need to express the answer in units of radians per second squared. Okay, so how do we calculate this? Well, to calculate angular acceleration, your angular acceleration is equal to your change in your angular velocity, which is delta omega, divided by delta t. Now, we've got delta t in seconds. We don't have delta omega. Now, we can calculate it easily, but we also need to make sure it's in its units of radians, because that's what it wants the answer in. So let's calculate delta omega first. You'd have delta omega would be equal to omega F subtract omega I, which would be equal to omega F is positive 210 RPM subtract positive 480 revolutions per minute RPM, and then this would give me a change in omega of negative 270. I'm going to write it down as revolutions per minute. So let's say it's RPM. I'm going to write down rev per minute. Okay, now I need to convert this into radians per second. So first of all, let's deal with the revolutions to radians. And here's what I know. I want to get rid of revolutions, so I'll put that in the denominator. Okay, how many radians are there in one revolution? 2 pi radians. Okay, so that's going to get rid of the revolutions units. And then I want to get rid of the minutes. So in 1 minute, I would have 60 seconds. So that's going to give me a delta omega that would be equal to, if we convert this correctly, it should be negative 28.27 radians per second. Okay, so that's how we do conversion from revolutions per minute to radians per second. Now we can just plug numbers into this equation. So in the equation, we'd have alpha would then be equal to, delta omega is negative 28.27 radians per second. So because we're slowing down, we have angular acceleration in the negative direction, which means it's going to be clockwise. So if you're moving in the, no, let's talk about that in a moment. Okay, so let's just calculate it. So 28.27. Then we divide by 4,440, and then we're going to get the angular acceleration. We're going to go to 2 significant digits because of that time. So we have negative 6.4 times 10 to the negative third radians per second squared. And what does the negative mean? The negative means our angular acceleration is in a direction that is clockwise. It does just want the magnitude, so the magnitude, we just drop the vector sign, in which case we can just say 6.4 times 10 to the negative 3 radians per second. Okay, so that's the answer. I did just want to point out, though, just the connection between what direction you're moving and whether you're speeding up or slowing down. So here's what we know. So initially, your omega is in the positive direction, which is counterclockwise. If your angular acceleration is in the negative direction, which is clockwise, then it tells me, since these two vectors are opposite in direction, it tells me that you are slowing down. So again, we're drawing perfect analogies between rotational motion and linear motion. Okay, this one's a little bit more involved. So it says the drive propeller of a ship starts from rest and accelerates at 2.90 times 10 to the negative third radians per second squared for 2.10 times 10 to the third seconds. And it says for the next 1.40 times 10 to the third seconds, the propeller rotates at a constant angular speed. And then it decelerates at 2.30 times 10 to the negative third radians per second squared until it slows to an angular speed of 4.00 radians per second. Find the total angular displacement of the propeller. Oh man, that was tiring reading all that out. Okay, the reason this problem is a little bit complicated is there's actually 3 forms of motion that are occurring. So we're going to break it down to 3 parts. So there's a first part where we are accelerating. So this would be part 1. There's a second part where we're moving at a constant angular speed. Okay, so that's going to be part 2. And then we decelerate, not a good word to use. When we say decelerate, we mean acceleration in a direction opposite to where you're moving, yeah, direction opposite to where you're moving, and that would be part 3. So we need to calculate the angular displacement for all 3 parts, then add them up, and then we can get the total angular displacement. Okay, so let's start off with part 1. Okay, we're going to say this is positive angular acceleration. Okay, so now it's just going to be, so we're talking about uniform motion here. So it's going to be exactly like solving a uniform acceleration kinematics problem, which means you need 3 variables to get the 4th one. Okay, so what do we know? We start from rest. So that is your angular velocity, omega I, is equal to 0. We accelerate at, so that's my angular acceleration. And we're assuming we're going in the positive direction. So my angular acceleration would be positive 2.90 times 10 to the negative 3rd radians per second squared. And we are doing that for a time t of 2.10 times 10 to the 3rd seconds. And we want to calculate delta theta. Okay, so we need an equation that has omega I, alpha, t, and delta theta in it. So this is going to be the same as the formula of the equation d equals vit plus 1/2 at squared. It's the only one that doesn't have the final velocity in it. But instead of writing d equals vit plus 1/2 at squared, we're going to write down delta theta instead of d. And we're going to write down omega I instead of vi. The t is still the same, plus 1/2. Instead of a, it's going to be alpha t squared. Okay, now we can get rid of this term because we don't have any initial angular velocity. So that's gone. Now we can just plug numbers in. This is going to be equal to 1/2 multiplied by the angular acceleration, which is positive 2.90 times 10 to the negative 3rd radians per second squared, multiplied by t, which is 2.10 times 10 to the 3rd seconds, all squared. And I'm just going to add an extra subscript here. I'm going to say delta theta 1. And that should be equal to positive 6,394.5. And we're dealing with units of radians. So I'll say rads. Now, before we go to part 2, so part 2 is we're moving at a constant angular speed. Now, the problem is, I'm going to do a calculation just before I go to part 2. We don't know what that constant angular speed is. So what I'm going to do is I'm going to calculate it right now, because the speed that we end this part at is going to be the constant angular speed for part 2. So we're going to calculate omega f. Okay, so whatever, if we start at an angular velocity of 0, we accelerate, and we end at this angular velocity, that's going to be the constant angular velocity for part 2. Okay, so we need to use an equation to calculate this. Now, I don't want to use the delta theta just in the event that I did it calculated incorrectly, although I did not, but I'm just going to assume that might have been a possibility. So in which case, we're going to use an equation that has omega I, alpha, t, and omega f in it. So which equation is that one? That's going to be the one that would be like having a translational equation of A equals delta V over delta T. So that would be, instead of A, you have alpha. Instead of delta V, you have delta omega. And we're going to divide this by delta T. We'll expand this to omega F minus omega I. And then divide this by T. Omega I is nothing. And then all we need to do to figure out omega F is just multiply both sides of the equation by T. So then I'd have omega F would then be equal to alpha times T. Let's plug my numbers in. Alpha is positive 2.90 times 10 to the negative third radians per second squared. Multiply by T, which is 2.10 times 10 to the 3 seconds. And then I'm going to get omega F for part 1 will be a positive number. And I get 6.09 radians per second. Okay, so we're going to make use of that in a moment. Okay, so now let's go to part 2. So for part 2, we're moving at a constant angular speed, and we're doing it for this amount of time. Okay, so I'm going to do the work on this page. So let's go back to a purple felt now. So part 2. Is going to be a constant angular velocity. Now, for a constant velocity, you'll remember that there's only one equation we can use. For constant velocity, we can use V is equal to d over t, which means that the equivalent angular equation would be omega is equal to delta theta, your angular displacement, divided by t. So that's all we can use. Okay, all the other acceleration equations are not applicable because we're not accelerating. Okay, so what do we know? We know the time. The time is 1.40 times 10 to the third. What's the constant angular velocity? The constant angular velocity would be equal to the velocity we finished part 1 at. So that's why I did that extra calculation in part 1. Otherwise, right now, I'd have to go back and do it. So I kind of set up the work in advance. And that was 6.09 radians per second. And we want to calculate delta theta. Okay, so the equation we use is omega, angular velocity, is equal to your angular displacement, delta theta, divided by t. So delta theta would be equal to omega times t, which would be equal to positive 6.09 radians per second, multiply by the time, which is 1.40 times 10 to the third seconds. And then you get delta theta would be equal to, I'm going to add delta theta 2 just to indicate it's the angular displacement for part 2. And I get positive 8.526 radians. Okay, now we're on to part 3. So part 3 is where we have the deceleration. Again, a bit of an evil word. We like to say in physics, acceleration in the negative direction. So I'll say angular acceleration in the negative direction. Okay, so now we're back to being able to use those acceleration equations. So what do we know? So let's go back and take a look. We know that the rate of acceleration is 2.30 times 10 to the negative third. Now that's negative. So 2.30 times 10 to the third radians per second squared. We also know, let's look at this here. We slow to an angular speed of positive 4.00 radians per second, although we're still moving in the positive direction. So this would be omega f would be positive 4.00 radians per second. It has to be positive, because if you're moving in the positive direction, your acceleration's in the negative, it means you're slowing down. If this is also negative, it means you'd be speeding up in that direction, which we're not there yet. Okay, now we seem to be missing one variable. However, we know what the initial angular acceleration is. The initial angular acceleration in part 3 would just be the angular velocity that we left at in part 2. So the angular velocity we finished at in part 2 was, because part 2 is a constant velocity, positive 6.09 radians per second. And we want to calculate delta theta. So we're going to use the kinematics equation that does not have t in it. So translational equation would be vf squared equals vi squared plus 2ad. Rotational will be omega f squared is equal to omega I squared plus 2 times alpha times your angular displacement delta theta. Okay, we want to calculate delta theta. So I need to do 2 steps to do it. First of all, subtract omega I squared from both sides and then divide by 2 alpha. So I'd have delta theta would be equal to omega f squared subtract omega I squared, divide this by 2 times alpha. Okay, and now we can start plugging the numbers in here. So omega f is positive 4.00 radians per second, all squared. Subtract positive 6.09 radians per second, all squared, and then divide this by 2 times alpha. So alpha is negative 2.30 times 10 to the third radians per second squared. Top will be negative, bottom will be negative. They'll cancel each other off because we're still moving in the positive direction. We're just slowing down. Therefore, our angular displacement should also be positive. So I'm going to call this one delta theta 3, and that value should be positive 4584.4 radians. Okay, now what's a total angular displacement? So your total angular displacement, delta theta, we'll say delta theta TOT for total, will be delta theta 1 plus delta theta 2 plus delta theta 3. Plug the numbers in. So delta theta 1 was positive 6394.5 radians plus delta theta 2, which is positive 8526 radians plus delta theta 3, which is positive 4584.4 radians. And now we're going to go to the correct number of significant digits. So delta theta total would be equal to positive 1.95 times 10 to the power of 4 radians. And the positive here means that we're moving in the counterclockwise direction. Okay, that's it for this lesson. So for this unit, I have a work booklet that contains fewer problems. Usually for AP work, we do fewer problems, although the problems are more difficult. So I believe in the rotational motion work booklet, in the rotational kinematics section, there should be, I think, 3 problems to complete. So complete those problems, and then later on, I'll just post I'm not going to post the full solutions. I'm just going to post the answers because I'm going to want to check out your solutions and mark them more thoroughly at a later date. But I will provide you the answers, just the answers a little bit later on. Okay, and I'll talk to you in the next lesson when we discuss calculating the center of mass in a rotating rigid body.